The old and the new. Artificial neural networks go deep. Deep learning's universal approximators that learn representations. But often the neurons, especially in the intermediate layers, are replaced by these function layers. Loosely speaking, deep means many layers. So shallow networks have only one hidden layer. So we tend to think of many layers. In other words, a deep learning model, DLM, is multi-layer. We have a representation component and a universal approximation. So that gives us something that looks like this. We go forward to get our predictions and backwards using our losses to update our weights. And the representations often are from the past 300 years or so of applied math. Calculus, statistics, we use all sorts of things for this representation layer before the universal approximation of the artificial neural network. So we're looking at very modern methods of approximation. And that requires special software libraries. Backpropagation requires derivatives, which means we use automatic differentiation. So we can go to this link for more discussion. But it also means that we get what are called compute graphs. For example, suppose we have z equals the log of xy. Well, I'm going to write w equals the log of xy. And notice I've got my forward direction, the x and the y are multiplied, and then that goes to some v that we take the logarithm of, and that gives us some w. And z is equal to w. But if z is equal to w, the derivative of z with respect to w is 1. So that doesn't contribute anything to the calculation of the derivative. So when we go backwards, we end up with this kind of a diagram. So we go backwards to get the derivative of the log, the partial z with respect to v to get the product rule, and then we apply that in this way. So here is another link that you can go to learn more about compute graphs in the software library PyTorch. So automatic differentiation and compute graphs, which means we're going to use tensors. So our functions are going to be from tensor spaces to the real line. And the feature space here is a tensor space. So the N1 to NP is column-like indexing, and the M1 to MQ is row type of indexing. So Rn is just one single upper index n. Rm cross n is two upper indices m and n. Rm cross n cross c is three upper indices m and c. Matrices have rows and columns, so an index for the rows and an index for the columns. Vector-like columns, functional-like, linear functional-like rows. And matrix multiplication generalizes to the tensor dot product. But we're not going to do much with tensor dot products. We should interpret tensors and use tensors as objects in a vector space. Sometimes they'll correspond to matrices, but we don't want to try to work with the concept of linear transformation or matrix decomposition. We simply want to think of tensors as generalized vectors in a vector space. So tensors are vectors in a vector space. Even the most complex data tend to be vectors in some vector space. A classical vector tends to have only one index, a magnitude in only one direction, often represented by a list of numbers. But a vector space is any set with operations of plus and scalar multiplication that is closed under linear combinations. And a tensor is in a vector space of objects with possibly more than one index, and hence more than one direction. So a tensor is intuitively a multi-indexed array of differentiable objects such as numbers with grads. So grad numbers, if I write the pair AB, I mean a plus b dx, where dx squared is equal to 0. This is kind of an algebraic assumption. We often just use epsilon, and so epsilon squared is 0. That's just a definition. But if f equals a, then df is equal to b, or df is equal to b dx, or b epsilon. So if I have f df times g dg, then that's fg, and then df times g plus f times dg. Now, I can actually show you that, because if I do this expansion, notice I get the fg plus the dfg plus the fdg. When I expand, I FOIL this out, plus the df dg. So g is p plus q dx, which is p plus q epsilon. This is bq epsilon squared at the very end, and so it goes away. And so we end up with this definition of multiplication of a function, or a number f, and its grad number df. And it's just the product rule. So grad numbers form a vector space. Tensors with the same size and the same differentiable objects are a vector space called a tensor space. So this isn't exactly how it's done in the software, but it'll give you some insight. Suppose we have 2, 3k. So this is, k is just a real number. And this is just a vector in R cubed, in R3. But with grad numbers, we have 2 plus dx, 3 plus dy, and k plus dz. So my dx here is 0, epsilon 0, 0, and dy is 0, 0, epsilon 0, and dz is 0 and epsilon at the end. So this is grad numbers for 3 variables. This is what we would look at. So we would get this expression. This is not a matrix, because the first row is grad numbers, the second row is grad numbers, and the third row is grad numbers. So this is a tensor, a T3-4 tensor. If I wanted to square 2, 3k pointwise, then that's the same as the pointwise squaring of 2 plus dx, 3 plus dy, and k plus dz, which looks like this. But the dx squared, the dy squared, and the dz squared are all going to have epsilon squares, and that's going to be 0. So we actually only end up with this. And therefore, we get another tensor, and it's another set of grad numbers, but it's the grad numbers for the square of 2 plus dx, 3 plus dy, k plus dz. Similarly, any smooth function from Rn to R can be redefined in terms of grad numbers as a function on tensor spaces. Order O meaning the order of the grad numbers. So all of this is implemented using machine learning libraries. The main two are TensorFlow and PyTorch. Both are based on compute graphs. They implement models similarly. The general forms of implementation: abstract definition of what we mean by a data set, code to define a model object, and we initialize an optimizer and a training loop until the expected loss is approximately 0. So deep learning, however, is only a subset of our problem-solving process. As we saw, deep learning includes computation and representation, but we still have feature engineering, and pre-processing becomes even more important. Feature engineering is still our most important task. Interpretation is critical, and we repeat this process over and over and over, as we've seen in the past. So pre-processing and model building. Our focus is on supervised learning, in which the goal is a model of the form the responses is f of x with some set of parameters or weights w. So this V is our feature space. It's a vector space. Can be any tensor space, really. But usually it's Rn for some n, although if it's got grad numbers, it's actually a tensor space. And we'll see Rm cross n. And going forward, that means that V is typically a tensor space. And we want to think of tensors making up our vector spaces. So grayscale images, we've already seen those. Color images, those are tensors. Now, what this means is we often get huge numbers of weights, huge value for Q. So the goal of pre-processing is to convert raw data into a vector space representation with features X. So what does feature engineering for deep learning look like? Well, it's actually a shared enterprise. So you coordinate with the deep learning model. You have to transform your data into a feature vector space, and often you have to do that yourself with independent of any deep learning algorithm. But also, you can get new features from the representations that are learned by the deep learning model. And sometimes the goal is to do this learning and then harvest the new features from the deep learning model. For example, linear algebra. If we do identity activation, this is not a universal function approximator, but if all the activations are identity activation, then the entire deep learning model reduces to just a linear algebra model. Surprisingly useful linear algebra models, very often the starting point for other things that we do. For example, multilinear regression. So we've seen this example in the past where we have a signal and we added some noise to it, and then we ended up sampling to get a training set and a testing set. And we want to fit it with this high degree polynomial model. Do feature engineering by hand. And then we have to do ridge regression. So we're going to look at multilinear regression. And the first thing you do in a deep learning approach is you create a data set structure. Now, I'm intentionally pausing right here and stopping because very often when you do these deep learning models, the most important part of your entire effort is in creating your data set structure. How you represent things in terms of tensors can often be more important to actual success than anything else. Also, we often build our data set structures on boilerplate PyTorch classes, so we can inherit a lot of nice features that we don't have to code ourselves. Here is a basic data set. It just inherited from the data set class in PyTorch. So much of the work is done in the init, the constructor. This is where we set everything up. For example, here's where we do our feature engineering. We did it by hand, manually. We actually using the scikit-learn polynomial features. And then we have to return everything as tensors, and PyTorch requires our tensors to always have at least 2 indexes. The rest of it's pretty straightforward. So next we define our training, validation, and test sets. So we're often given the test data as a gold standard, but here I'm assuming we have the X-train, Y-train, X-test, and Y-test. And that signal data set, that's just going to be what we use to compare to the actual signal structure itself. Now this data set structure doesn't redefine the data, it simply defines how the data is going to be transformed into our tensor representation for our machine learning model. So it applies a structure to the data. And it turns out to be a pretty simple structure, but it's tensors. So we have an observation of the features and then a target value. Then we define data loaders. Now these are very useful. They're optional, but they really, I encourage you to use them because they really help you manage your data, how the memory is used by the data set, lots of things that you do with data loaders. And then we define our model. So once again, we're going to inherit from torch.neuralnetwork.module because that means we get everything, in particular, the back propagation, which I don't define here. It's built in. Once I have a forward, then the backward is already there because it inherits the backward from the torch.nn.module. So here's my model. And then I want to define a loss function and choose an optimizer. And then we're going to do a training loop. Training loop looks something like this. Our forward is to get a prediction, and then we calculate our loss. In PyTorch, you have to zero the gradients. I don't understand why, but if you don't, it'll add the new gradients to what's already in the gradients, so you zero them out. Then the backward step calculates derivatives with grad numbers, and then you take a step. And then you're just back to the standard data science world. So back to scikit-learn and comparisons and predictions and the Polya problem-solving process. So here was our model, and notice that our tensor from our model state dictionary, now we have these values for the weights. And we actually can get a pretty nice prediction that's some reasonable approximation of the actual. So what advantage do we have over ordinary multilinear regression, you might ask? Well, the old plus the new. So we could actually learn the best moving average for reducing the noise in the data before we do multilinear regression. So deep learning, artificial neural networks are universal approximators, but we have 300 plus years of fantastic math and science that have revolutionized every aspect of our lives. Deep learning models allow us to combine that 300 plus years of fantastic success with the promise of artificial neural networks. The old plus the new. Doing so requires a new type of software library, has to be fast and efficient, and has to calculate derivatives exactly, and does so. So they tend to rely on vector spaces of tensors instead of just simply a standard vector space of columns, as we've seen in the past.